Hello and welcome to the Chapter 11 practice problems. I'm going to be going through these in a little bit more detail than I previously do. So this first video I'm going to cover questions 1 through 8, and then I'll do another video going over the remaining questions for time purposes. So let's begin. So going through each question here, the standard deviation for t-distribution is exactly equal to 1. That is false. It is not equal to 1. It's actually a little bit bigger than 1. You can find this in your book on page 240 if you are interested in reading more. It's at the very bottom in the footnote. Question 2, using a table for reference, determine the t-value of T10.95. So remember, T10, this is your degrees of freedom, and this is your cumulative probability that we can find in the back. So in order to find this, you go to table B in the very back of the book. If you haven't already done so, I highly suggest putting a sticky tab or a post-it note or something back there to get back to the tables fairly quickly. The way you find this is you go to your table C, go to degrees of freedom 10, which is found on the left-hand side, go all the way over till you find the very top portion of cumulative probability of 0.95. And when you find that, you meet them up and you should get a value of 1.812. Do the same thing for the t-value of t degrees of freedom 14, cumulative probability of 0.99. When you do that, you'll find the value 2.624. Question 4, which of the following correctly describes the relationship between a standard normal and the t-distribution? So we're looking at the two different types of distributions we have here, the standard normal distribution and a t-distribution, and which one is the correct relationship between them. So the standard normal is an approximation to the t-distribution. Answer is incorrect. The standard normal is not an approximation to the t is an approximation to the standard normal. B, as the degrees of freedoms increase, the t-distribution approaches the standard normal. This might be true. It is true, but let's read the other ones. As the degrees of freedom decrease, the t-distribution approaches the standard normal. That is incorrect. And the t-distribution is the inverse operation of the standard normal, and that is also incorrect. So the correct answer here is B. A researcher is interested in the effectiveness of a new program at reducing the average systolic blood pressure in a population with a new hypertensive medication. The researcher wants to test the hypothesis that the mean difference in the systolic blood pressure is greater than 40 mmHgs. Which of the following represents the correct null and alternative hypothesis for study? So remember, our null hypothesis when we're comparing differences, most time will probably be 0. Every once in a while there might not be. For example, this one here, and we're calculating the mean difference. Anytime you see mean difference, think of that delta, right? So we're going to be mu delta. So if we're looking for mu delta, we can already kind of cross out 1 and 2. That is not what we're looking for. We're looking for the difference between the groups. So we're going to be between C and D. And when we're looking at this, we're looking for a hypothesis that's going to be greater than 40. So if you look at our alternative hypothesis, we have mu delta, mu delta. This one is not equal to 40, and this one is greater than 40, and that's what we want. We're looking for a mean difference of greater than 40. So we have C. Suppose the researchers are interested in a program that is intended to reduce overall calorie intake in a group of women looking to lose weight after pregnancy. The program manager sets a daily calorie count intake limit of 2050 calories a day. Which of the following represents the null and alternative hypothesis representing a two-sided, so let's underline that, two-sided one-sample t-test for the average calorie consumption in the weight management program? All right, so if we're looking at two-sided, we know already that our alternative hypothesis is going to have a not equal to sign right, because that's the only way we can have two-sided. If it's greater than or less than, it's not going to be a two-sided. Those don't count. So it has to have a not equal to sign. And if you look just out of all the possibilities given to us, well, we know, like I said, it has to be the not equal to sign. So there we go. There's your correct answer. That one's pretty straightforward. You can also look that B can't be it. Right here is not equal sign. You can never have a not equal sign in your null hypothesis, and null hypothesis is always going to equal a value. And we're not looking for the less than or greater than value here, right? Because it's already asking to find a two-sided alternative hypothesis, so our correct answer has to be D. So 7. So suppose a researcher is interested in the effectiveness of a new novel talk therapy technique in reducing overall depression as identified via score report on the generic depression scale, or GDS. In order to carry out this hypothesis, the researcher gathers a simple random sample of participants in the program, performs the GDS test prior to and after initiation of the new therapy technique. Assume the simple random sample score report presented below represents an approximation normal distribution. So before we even get to what they're asking us for, there's already a lot we already know. We already know that we have a prior and following test, so think this is a pre and post test, right? Where we have participant A, B, C, D, E, F, right? So we have N equals 6, we have 6 people. And we know that participant A took a pre-test and a post-test. And here's their values. They are matched, they are paired. This is what has to be done in order to do a paired sample. And we're trying to find a new therapy technique. And so, but the technique is in reducing overall depression. So we want to score lower on the depression scale. If this actual new novel talk therapy technique actually works, it's going to reduce it's going to reduce the score of depression. So we know our alternative hypothesis is going to be less than. That's what we're trying to score, but in reality, we don't know if we're actually going to score that. So, but moving on. Now we can kind of go to part A. So what type of test design is this? Well, we already know. You can say paired or pre-post test, right? This is paired, match, pre-post test. This is the type of test it's doing, right? And then the second part wants us to conduct a paired sample t-test, right? So it's already given to you here what kind of test it is. We have to do a paired sample t-test. Investigating the effectiveness of the new therapy technique with 95% confidence. Write out your null and alternative hypothesis and interpret your p-value correctly. All right. So for here, we're using delta, right? We're trying to find the difference. When we're using paired sample, we're going to try to find the difference using delta in between. So our null hypothesis for this one, we don't know whether the difference is going to be higher or lower, but we want there to be a difference. So our null hypothesis is going to state that mu delta, that is not a very good mu. I'll try to be a little bit better with these. Mu underscore delta is going to equal 0, right? That's stating that the difference between the group is none. There's no difference between the group. An alternative hypothesis, since we don't know if it's actually going to be higher or lower, we can't really say. We can say which way we want to go, but we're going to run a two-tailed test here for this one. So we're going to say our mu delta does not equal 0. Now you can say mu delta, mu delta, it's going to be greater than 0 or less than 0, showing there's going to be a difference between the group, but really we don't know, and the two-sided test is what you're mostly going to always encounter when we're running a t-test. So that's our null and alternative hypothesis, and now we have to interpret our p-value. So in order to get a p-value, we have to first run our t-statistic. In order to do our t-statistic, let's write our formula. So our t-stat is going to equal our x bar delta minus our mu delta over the standard error of x delta. So the way we calculate this is you have to come up with your delta. So the way we're going to do this is you take 12 minus 8, and you're going to get 4. And you do this all the way across. 6, 5, 5, 5, 4. Now these are all your new data sets of delta. These are your new delta sets. Add this all up. 29 divided by 6 equals 4.8333. This is now our x bar delta equals 4.8333. Then you can take your x bar now and go to your delta set and calculate your standard deviation, taking minus 4.8333 all the way down x bar delta minus x bar delta minus x bar delta. In the convenience of time, I'm not going to do all the standard deviation part of it, but when you're done, you should get a standard. So your standard deviation of delta should equal 0.75279, right? And when we want to calculate our standard error of x, remember standard error of x is going to equal the sorry, I put the page on the wrong side here. The standard error of x is going to be your standard deviation divided by the square root of n, standard deviation over the square root of n. When you do this, you're going to have your 0.75279 divided by the square root of 6, and you get a standard error of 0.3073. Now we have all the parts we need to get our t-value. So our x bar delta is 4.8333 minus our mu delta is 0, divided by the standard error of x, which is found here, 0.3073. Once you calculate all that out, you will get a t-stat. So this is going to equal your t-stat of 15.7283. If you get a slightly different answer than what I'm coming up with, but are still within like this 15.7 range, it's completely fine. It all depends on rounding, right? If you did all 5 digits here, some people are heroes and like to go out like 8 digits. Some people will round this to be 0.7528. Depending on how you do it, this answer is going to vary just a little bit. But as long as you're around this 15.72 area, that's going to be good. So what does this t-stat tell us? This t-stat tells us that we're about 15.7 standard deviations away from the mean with this information provided. So we know we're pretty far, but truly we need to find it in the back of the book. So when you go to the back of the book and go to your t-stat, you're going to go and find your degrees of freedom, which is n minus 1, so 6 minus 1 is going to equal 5, so degrees of freedom 5, so you're going to go degrees of freedom 5 at 95% confidence, and you're going to try to find a value of 15.72. Well, when you keep going on the degrees of freedom 5, you'll see that there is no 15. Remember that the back of the book, those tables expand infinitely in both directions, and so you go to the highest value you have there, which I believe is like 6 something, 6.869, and so our 15 is greater than that. And as we expand out, we know our p-value is going to be less than 0.001 or 0.002 if we'd even do 2 tails, but it's going to be even less than that. So when we look, we see our cumulative probability 2 tail. So I'm going to put probability of 2 tail, PTT, is going to be less than 0.001. Even if we multiply, if we have a two-sided test for find a few value multiplied by 2, even if we multiply this by 2 and get 0.002, even at an alpha level of 0.05, right? If we have confidence, 95% confidence, alpha equaling 0.05, we're going to know that our p-value is less than alpha, so there's significance there. On the back, when we go to the t-tables, remember those charts expand both ways, and we're never going to find an exact value unless you have a calculator. So the best thing we can do is if we fall in between intervals or are greater than or less than intervals, we can determine that we're greater than or less than at a certain probability or in between probabilities, and that's the best we can do with the charts we are given. When we're trying to construct a confidence interval, for this. I think